Hi everyone. My presentation is on energy efficient network routing using hybrid quantum algorithm. It is a joint collaboration among researchers in the US, Ireland, and UK. Part of the presentation content has been presented in the Adiabatic Quantum Compute 2021 conference. The content of the presentation is as follows. First, I'm going to talk about the motivation of the work. I will discuss the pending issues, energy efficient routing. I will also discuss conventional approaches that researchers have used to tackle them. Then I will show the formulation of a problem in the work. I will explain how to solve it by illustrating a simple example. Next, I will discuss about the result that we have obtained. In the end, I will propose the future work to be carried out. So when we speak, people at a longer distance away will be more difficult to hear our words correctly. It is due to the signal attenuation distortion in the open air. In wireless communication, the system has a transmitter receiver at each end. When the transmitter tries to convey a message to the receiver, the air channel will be deteriorated by amplitude and phase. The former leads to the path loss, while the latter leads to Doppler effect. In order to counter back amplitude attenuation, power control mechanism has been implemented in NIC-LIG protocol. It is to adjust transmission power to higher volume if the distance is longer, and to lower volume if the distance is shorter. In the meanwhile, in order to execute administrative check and task scheduling, the devices themselves need energy to process and hold data signals. In all, communication routing consumes energy. Somehow, energy supply is usually volatile and a shortage many use scenarios. For example, in smart home and city applications, how to save power in order to cut utility bill might be of most interest to end users. Furthermore, in wireless by-body network, the devices are usually battery powered with limited supply of energy. How to optimize energy consumption poses urgent question. The state-of-the-art computational tool for large-scale optimization problem is high-performance computer. A branch of research in it is parallel and distributed computing. It is of common sense that multiple cores runs faster than single core. Somehow, how to schedule and coordinate them is a big tricky issue. The state-of-the-art computational method is sophisticated software algorithm design. I categorize this design into two kindreds. One is biointelligence, take game theory, neural network, sport intelligence, for example. The other is artificial intelligence, take learning theories, for example. Softwarization raises the challenge to these conventional approaches. First, there emerges high volume data process. In lower ISO layer, softwarization gives rise to digitalization of the legacy hardware infrastructures, for instance. To our best knowledge, the network topologies in many situations are abnormal. In higher ISO layer, softwarizations open the door to myriad applications, video games, for example. Second, as the barriers to enter the playground has been lowered, a pursuit of extremity has been pushed forward. So my project highlights is below. It is first to apply the computational power of QPU, quantum process unit, to network design, particularly in the utterly important direction of energy conservation. It is also the first to compare 2000Q advanced system processor performance in the application network design. And it is first to apply domain-aware encoding scheme for QPU in practical engineering problems. So in the figure at the upper right corner of the slide, each dot represents a device in the mobile system. The black dot is the source device that has a transmission task. The red dot is the destination device that has the receiving application. The gray dots are the relays on the way. In the figure, we pinpointed 3 feasible paths from the source to destination. Intuitively, you can tell that it is easier to compute which path consumes the least energy. But how about increase the number of the source nodes or the pool of potential relay nodes to add the computational complexity? I'm now giving an example of 2 source nodes transmission scenarios on 6 nodes graph. Suppose nodes 1 and node 3 are transmitting at rate 1 and rate 3 respectively. Node 1 has 2 path options. The first one is edge 1 and edge 2. The second one is edge 1, edge 3, edge 5, edge 6. Node 3 has also two path options. The first one is edge 3 and edge 2. The second one is edge 5 and edge 6. The source device and destination device only consume transmission processing energy and receiving energy respectively. The relay devices consume both the transmission and receiving energy. We use indicator vector of size 2 for each node. It indicates whether the corresponding path is selected or not. So there will be 4 possible combination paths. Suppose we selected both the first path of each node. Then edge 1, edge 2, and edge 3 are in use. The traffic from node 1 goes through edge 1. The traffic from node 3 goes through edge 3. The traffic from both nodes 1 and node 3 goes together through edge 3. We have to make sure that edges are not overcrowded. Overloading the edge will lead to packet drop at the transmitter end. The hybrid algorithm has 4 steps. First, we collect all passes given a determined graph and traffic dynamic. Second, we assign the passes to respective edges for convenience of computing energy consumption along each path. Thirdly, we formulate the QPO problem and encode it. Finally, we submit the problem to the QPU. So we devise 3 performance metrics to evaluate the QPU. We have corrector rate, the number of probe instances that reach the minimum energy processing time to the overall number of probe instances. In corrector rate, fraction of the samples which return a solution that is not optimal. Embedding error rate, fraction of the samples which fail to be embedded. We also have effectiveness plot and speediness plot. Effectiveness plot is how badly and well the respective QPU performs in terms of accuracy against classical solvers. And it shows the correct rate, incorrect rate, embedded error rate. Speediness plot is how well and badly the respective QPU performs in terms of speed against all classical solvers. And it shows correct rate. And we have 2 categories of experiments. First, it goes over all possible combination of graph size and source number excluding the flow rate. Second, we apply Erdos learning algorithm generation algorithm and generate 20 problem samples per graph size from 5 to 12. For the graph size equal to 5, the results are obtained from analysis over all probe instances that the QPU time limit allows. We can see that a majority of the QPU problem has size 5. The size of the bubbles indicates the number of the QPU problems with the same size. We can tell that advantage system has absolute advantage in the speed when the QPU size increases to around 10. The QPU stops functioning with the QPU size reaches 20 and above. For QPU size below 10, QPU has a dominating effective accuracy. Then we evaluate performance metrics against the number of source devices. First, we can tell that correct rate decreases piecewise linearly as the source number increases. Then 60% and above samples are solved faster by the advantage system than 2000Q and classical solvers. Finally, no embedded error exists across all the samples.
So we do a comparison of the processing time. We found that for a very high percentage of problems, QPU performs faster than classical solving in general. And also in a general view, advantage system performs faster than 2000Q, which is faster than Groupie, which is faster than Cplex. To be precise, for 2000Q, given a fixed amount of number is equal to 5, the processing time for all the problems are the same. It is around 0.0025 seconds. For advantage systems, given a fixed number is equal to 5, the processing time fluctuates. It is around 0.001 seconds.
Cplex solving time ranges from around 0.112 to 0.2. Groupie solving time ranges from around 0.1 to 0.12. 2000Q lags behind Cplex and Groupie in some probe instances. Advantage system stays ahead of Cplex Groupie in most of probe instances. And we have also done experiments for the graph size equal to 5. We have found that probe instances that are feasible for submission to QPU size is all 5. QPU demonstrates absolute advantage over classical solvers regarding solution quality across all the problem space. With number reads per round set to 3,000, QPU doesn't show an advantage in the speed, while with number reads decreased to 5, QPU speed overrides those by the classical solver without degrading the solution quality. Next, we will show the results from the graph generated by Adolph's learning algorithm. The figure on the right-hand side tells that average QPU size decreases as edge property increases. And the figures on the next slide will show the following statements. First, performance degradation point move rightwards as edge property decreases. Then the embedding error appears at large graph sizes with lower values as edge property decreases. Finally, advantage system shows absolute advantage in speed over all the other three solvers. To be more specific, we can tell that for probability equal to 0.9, the performance of both advantage system 2000Q starts to degrade at graph size 6. Somehow, 2000Q starts to report embedding error where the graph size reaches 7, while advantage system starts when the graph size reaches 9. In between graph size 6 and 9, advantage system is able to return solution that is not guaranteed to be optimal. 2000Q completely failed to embed the problem at graph size 9, while advantage system at graph size 11. Similarly, for probability equal to 0.7, performance of QPU starts to degrade at graph size 7. After that, 2000Q starts to report embedding error. At graph size 11 and beyond, 2000Q failed to embed all the problem instances. There exists no cases for less optimal solution to appear for 2000Q. For advantage system, at the largest graph size 12, 80% problem instances are failed to embed. For the rest, the solutions are not optimal. Embedding error appears at graph size 11 and beyond. Finally, for probability equal to 0.6, the performance of QPU starts to degrade at graph size 8. Beyond that, 2000Q starts to report embedding error, and the portion of samples with optimal solutions gradually decreases. At the largest graph size 12, the embedding error rate for 2000Q has reached as high as close to 100, while for advantage system, it is just around 20%, with a larger share of the problem instances reaching suboptimal solutions. The next four plots show the average processing time for graph size for QPUs and classical solvers, respectively. We excluded problems where embedding errors occur at the QPU. We will notice that the plots of the processing time for classical solver has similar patterns, respectively. As with the same with what has been observed from previous plots, 2000Q shows a constant processing time on average, while for advantage system, the average processing time goes up when the graph size increases, but stops increasing at a certain graph size and beyond. For edge probability equal to 0.9, this occurs at size 9. For edge probability equal to 0.7, this happens at size 11. While for edge probability equal to 0.6, we cannot see this effect and hypothesize this may happen beyond size 12 or experiment graph size upper limit. From previous figures, we have come to agree that for edge probability equal to 0.9 with graph size larger than 9, only probe instances that are easily complicated, or those below graph size 9 can be embedded well onto the QPUs and return valid solutions. The similar conjecture can be applied to cases where the edge probability is less with larger turning points. For the point phenomenon that average processing time is lessened for even larger graph size, we suspect the graph size alone cannot determine the complexity of the network. Other factors take effect, such as the structure of the network. The C+ average processing time seems to correlate less than with graph size and edge probability, while for Groupie, plots show that average processing time goes up as the graph size increases in general and with larger edge probability. If this trend continues, it suggests that for larger problems, there may be a crossover where C+ becomes more effective. So first of all, I will do network scaling and just investigate the possibility of application of quantum walk algorithms. And in the even more future, we will investigate it into early prototype and test network resilience against dynamic change of the network traffic. So the experiment configuration is as follows. Thank you for watching this presentation. Thanks for your time. And if you have any questions, please contact me as jia.chen@durham.ac.uk. Thanks a lot.